Hi, I'm Regina, and this is my Lab 4 on magnet braking with Faraday. For this lab, I've split it up into the introduction and experiment details. The following listed are the purpose of the lab: to explore the interaction between a falling magnet and its induced current, collect data of a falling magnet through an aluminum foil tube, to computationally model a magnet and tube interaction, and then to compare computational predictions with the observed data. Models and fundamental physics principles include the magnetic field of a bar magnet, the magnetic field, the magnetic flux, force on loop due to a bar magnet, change in magnetic flux from a moving dipole, Faraday's law, and the magnetic force. Newton's third law explains how the force on a loop on a bar magnet is equal and opposite from the bar magnet on the loop. After Faraday's law, we have Lenz's law, which tells us that the magnetic field from an induced current will point in the opposite direction of the change in flux to restore the original conditions. Experiment summary. Mark the north pole of the bar magnet, hold the tube vertically, and put the bar magnet above the top opening. Record the magnet being dropped through the tube, calculate the time it takes for the magnet to fall through the tube, and then repeat this procedure 5 times and calculate the average time it takes for the magnet to fall through the tube. The following are a preview of the results. The system was the aluminum foil and the bar magnet, while the surroundings was everything else. The average fall time I'd calculated was 0.991 seconds, while the computational model fall time was 1.242 seconds. Why foil versus a ferrous tube? Ferrous materials would have interfered with the bar magnet, and aluminum is not magnetic, so the bar magnet can easily fall through the tube. And one of my observations was that the magnet falls slower than if it fell in a free space. Now on to experiment details. The following data is pertained to the system. So I have the aluminum foil, the length, width, and inner radius of the tube, and for the bar magnet, I recorded the mass and the magnitude of the magnetic dipole moment, which I got from my previous lab. For the computational model, these were the constants, and then I input the tube geometry to match my model, then the properties of the bar magnet, and lastly, these were the initial conditions. Next, I input the function to calculate the magnetic field of a bar magnet, then input the function to calculate the magnetic flux. To the left, you can see the code for the magnetic force, and then on the right-hand side, I included the gravitational force, net force, and the magnet's velocity and position. Here are my results. So the measured time in tube for the real-life experiment was 0.991 seconds, and the time in tube for the computational model was 1.242 seconds. So what's the difference between the model versus the real-life experiment? Well, the model can be more accurate if air resistance was considered and used more rings to represent a tube rather than a collection of rings. So what happens to the system when you flip the magnet around? Well, the time spent in the tube would actually be the same, and the directions of the magnetic field and current would be the opposite. Here I included a screenshot of currents moving downwards with the falling magnet. So how do you know which current represents which color? So the red represents the counterclockwise current, red is north, and from the bar magnet is creating a magnetic field downwards, as by the right-hand rule. And the blue represents the clockwise current, blue is south, and induced current opposes change in the magnetic flux from the bar magnet. Once the computational model was run, this graph represents what happened to the magnet. So in the graph, there's a negative slope because the force of gravity was stronger than the magnetic force of the aluminum foiled tube, and the slope then zeroes out and experiences a constant velocity due to the force of gravity and magnetic force from the foil tube canceling each other out. Some possible errors could have been human error in the analysis of the video, inaccurate measurements of foil and bar magnet, or incorrectly calculating mu from the previous lab experiment. Now for the discussion. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Induced current and magnetic force would increase due to Ohm's law. Since there would be more force counteracting gravity, the magnet would fall much slower. Now, what if holes or slots were cut into the tube? How would this affect the ring current in your model? The induced current and magnetic force would decrease. The magnet would fall faster if there's less force counteracting gravity. Lenz's law wouldn't be as powerful here. Ultimately, in this lab, I was able to see how a bar magnet can induce a magnetic force and apply concepts such as magnetic field, flux, Faraday's law, and etc. This lab allowed me to experiment and computational study Faraday's law to facilitate an understanding of this in action. Thank you.